All right, well, it's 3 o'clock, so since I am supposed to be running here at 3, we'll go ahead and get started. Thanks to everybody who came in, and hopefully you are in the right place. My name is Mike Anderson. I'm Chief Scientist for the PTR Group. I've been in the embedded systems business now a little over 35 years. My first embedded machine was actually an IBM mainframe doing radar processing. But it was actually, we even thought it was real time because it was faster than the radar sweep. So real time and embedded doesn't necessarily mean small. In this case, however, we're talking about things that are reasonably small to some things that can be absolutely downright big depending on your perspective. So we're going to talk about building Linux-based robots here. There are several different approaches that we can potentially take to build a robot. And we also have to understand exactly what it means when we say we have a robot. There are lots of different interpretations depending on what you're trying to build. And my particular company, we are currently involved, and I'm up to my neck, in building space robots. So how cool is that, right? We actually are part of NASA's program to do space refueling of weather satellites. It turns out that the GOES satellite is, we had a GOES satellite that got hit by a meteor, took out the weather coverage over the US. They had to move the satellite over the Pacific, over the US, in order to get weather coverage. And when they did that, they burned all the station keeping fuel. So we've got a few more months before that satellite runs out of fuel. And when it runs out of fuel, we lose weather coverage over the US. So it's a little important. And what we're trying to build is, and I'll actually show you a couple pictures. We're building a set of flight software and robots that will literally go up, see a satellite, grapple it, unscrew the filler cap, and refuel it. And then wipe the windows down. For those of you who are old enough to remember people who used to do that. All right, so we're going to talk a little bit about what a robot is, some basic services, how we deal with mobility, and of course the sensor packages. And then we'll finish up, we'll talk a little bit about robot software frameworks, which ones are available to us in the Linux world, and we'll hit it with a quick summary. So if you want to make a robot, well, that's cool, but we need to know exactly what that means. And generally, if you look at definitions, robots were originally defined as a mechanical intelligent agent. So we have automatons. These actually, the first robots actually go back into the 1500s and 1600s with very clever clockworks and fully motion automatons. So they're kind of cool looking if you ever see one of them. I've seen them over in Europe a couple of times in some museums. Today, these are generally electromechanical devices. So they're usually guided by some sort of computer. We have some programming that's involved. The language is really immaterial as far as that's concerned. Many of us use C and C++ because we want to be able to get as close to the metal as possible. But certainly Python, Java, just about any other language is certainly possible. There's some definition issues there. Some people believe that you really only have a robot if it's capable of doing autonomous operations. That is something without a human in the loop somewhere. A lot of others say, well, really teleoperated, just because you've got an operator in the loop doesn't necessarily mean that it isn't a remote bot. It's a robot, but it just happens to have a human in the loop that's controlling everything. So depending on how you interpret that, you might say that it's a robot, or you might say that it's just a teleoperated device. It doesn't really matter when you get ready to start making one of these things, because we can take something that's teleoperated and then add the additional intelligence to make it fully autonomous. And that's kind of the goal for a lot of these gizmos that we'll be talking about in some of the pictures you'll see. We want to make things as autonomous as possible because, quite frankly, certainly in the case of my situation where we're dealing with things in orbit, the time delay to get to geosynchronous orbit, which is 24,000 miles away, is sufficiently large that you cannot actually teleoperate the robot. It's got to be pretty much fully autonomous. We just simply give it a command and hope that it does the right thing. Of course, the worst case of that is what's happening right now on Mars with the Curiosity rover, because it's got a 20-minute round trip time to get to Mars and back. All right, so when we talk about robots, we talk about different classes of robots. First of all, of course, mobile robots, things that aren't fixed to the floor. We have industrial robots that typically are fixed to the floor. This is where we would see the typical assembly line, for instance, in an automobile manufacturing facility. And then we have service robots. Now, service robots can be either semi or fully autonomous, kind of your classic service robot these days that most people have at least heard of, many of us have, are the little Roombas that go and sweep around the floor. I have cats and dogs, and if it wasn't for the Roomba, we'd be overcome by hairballs all over the place. It's just, ugh. And I'm allergic to it, so it makes it all that much worse. And more important for the robot, yeah?
Do cats stalk the Roomba?
They have. The dogs like to chew the Roomba. And so I got one of the ones that has the mop in it, the water, and it squirts them. So that's, and actually I want to hook up a little control on that one. So, all right. But this is what many of us think of when we think about robots. We have anything from the kind of classic battle bot to the helicopters, a lot of mobile platforms here these days. This one actually has a paintball gun thing attached to it. And I've seen them that have airsoft guns attached to them too, just for chasing people around and shooting each other. So it's kind of fun and non-lethal, so that's good. The general characteristics of any robot that we're going to produce here, they have several things in common. First of all, we're going to have a task, something for it to do. Whether it's a remotely operated vehicle looking for things underwater, whether it's a space robot refueling satellites, it usually has some purpose, even if it's nothing more than entertainment, kind of like this guy here. We'll have the issue of whether it's autonomous or teleoperated. And in some cases, autonomous is easier because you don't have to worry about the communications links. With this particular one, teleoperated becomes a bit of a nuisance because of some issues with the Beaglebone. We'll talk about those later. But autonomous can be easier to implement if we know exactly how the thing is supposed to behave. That is, if we have a closed-loop feedback system so that we have repeatable behavior, then fully autonomous behavior is not that difficult to implement. We just have to know what the movements are supposed to be and the range of the sensors that we're working with. The frame. Clearly, we're going to have a frame of some sort. The question is, what's it going to be made out of? We have mobility issues. If it's going to be a mobile robot, then are we using tank treads? Are we using wheels? What are we using? Is it a hovercraft? Those are really difficult to work with. I built a couple of those. They're really scary because once they start going, they can't turn very quickly. They keep kind of sliding. Of course, the hardware controls, how are we going to steer it? The sensors, what are we going to do in terms of figuring out where we are in the world? We have to have some sort of model inside of the robot as to where it is in space and time. End effectors, of course, how does it manipulate the world? Do we have an arm? Do we have some set of tools that we have to work with? How are we going to power it? Now, that actually becomes one of the more difficult problems to deal with. And the folks at the TSA just absolutely loved my bot going through security because it's got an 8,000 milliamp LiPo battery. And those things become bombs if you don't treat them nicely. So, although I didn't say that to the TSA. But, oh no, it's just a robot battery, no problem. And of course, the software controls. How are we going to actually take information from the human and then translate it into something that the robot can understand? So when we take a look at the frame, and oftentimes wood is a nice place to start. I'm a mentor on a high school robotics team, Team 116 from the first robotics competition. And oftentimes we will prototype with wood or PVC pipes, just simply because they're quick and easy to put together, they're light, they're very flexible, so if you hit something, it's not going to bust up. And there's a lot of advantages to wood and PVC. Aluminum, of course, tends to be the material that we work with most often, because it's light, it's strong. We get a lot of advantages from using aluminum. Although you have to be careful about grounding issues, because you can't have a grounded chassis, and that could be very disastrous if you got a hold of the wrong wire. Steel, there's a lot of devices, a lot of robots out there that are made with steel. These are typically bigger military robots, tend to be made with steel. They may be as much as 10 gauge, 12 gauge cold roll steel, effectively bulletproof kinds of things. But those are really heavy, very difficult to work with. The power plant to make those things work is not very easy to work with. Titanium, that would be great, but titanium is outrageously expensive. So it really boils down to what kind of tools do you have at your disposal. If you've got a typical woodworking shop, you have hacksaws, things of that sort, you can typically make wood or aluminum without too much trouble. But if you're going to be doing anything sophisticated, then you may have to have a mill or... actually, today, we're doing a lot of 3D printing with our parts. So that's a fantastic thing. We love the 3D printed parts. The one thing I would say to watch out with 3D printing, especially with ABS plastics, don't get blue Loctite on the ABS plastic. It disintegrates almost instantaneously. Really nasty. So especially when you're depending on that part to do something and somebody got a little sloppy with some blue Loctite and they just go, that's a technical term. All right. We have to worry about weight. How much are we going to be able to move around with this thing, considering the motors that we have access to? There are a lot of commercial robot frames that are available to us. There's a few of them listed there. This one happens to be a commercial robot frame called a Wild Thumper. This one's a 6-wheel drive. All 6 of the wheels are independently suspended. All 6 of the wheels are driven with motors. But this particular robot pulls on the order of 15 amps per side. So we'll pull on a full load before stall current. We're looking at about 30 to 40 amps being drawn on this little robot right here. It's a very powerful robot. It's very fast, and that's why it pulls so much power. But you definitely have to think in terms of what your power plant's going to look like as you're building it. Should it be wheeled or tracked? I mean, we love to think in terms of, ooh, if we're going to put tracks on it, then it'll be invincible. It'll be able to climb anything. Well, yes and no. The problem with tracks are that when you start to turn with tracks, there's a lot of scraping force on the track. And if you don't have the track fully seated and set up in such a way that it won't pull off as soon as you start to turn, especially if you're trying to turn on carpet, carpet's terrible on tracks. It just will take the track right off. Tracks are heavy. The support mechanisms, the tensioners, everything else that goes along with tracks. They're cool looking, but they're heavy, they have a scraping force problem, and they're not quite as mobile as what we get out of wheels. Wheels, we have 2-wheel drive, 4-wheel drive. This one happens to be 6-wheel drive. They're very fast, they're maneuverable, they've got good climbing ability as long as it's nothing too steep, like stairs. 6-wheel drive can, in fact, this one actually can do stairs, but not really tall stairs. There's lots of other techniques that you can use for carrying stairs, for doing stairs. But the nice thing about having multiple independent motors is that you can have 1 or 2 of the motors fail, and it still is mobile. That's a good thing. You don't want your robot stuck someplace. We've tinkered around a little bit with a service bot, basically, that searches for people in destroyed buildings. So if there's an earthquake, how do you find somebody? Well, you can actually send a little robot in there that actually can get into smaller places than a dog can. And we've got some very good sensors, CO2 sensors and methane sensors, other things that we can then use to detect whether there's still people breathing in there. So it's actually quite a bit of things that we've been successful with in terms of 6-wheel drive systems. The steering approach. There's a lot of really interesting steering approaches. The one that we use most commonly is this one called skid steer, aka track drive, tank drive. If you've ever seen an old World War II movie and you see the guy kind of cranking the handles and the tank kind of moves like this, that's tank drive. It's very difficult to explain that to high school students these days because none of their vehicles work like that. Even the M1A1 tanks now look like a motorcycle. So they don't steer the same way that we used to with the old tanks and tractors. But that's very simple to implement. You have Ackerman drive that drives just like your car does. Problem with Ackerman drive is you have to have planetary gears to keep the wheels from locking up on you, especially if it's four-wheel drive. It's just like having a four-wheel drive truck that the hubs are locked on dry pavement. Doesn't work so well. So Ackerman drive, you have to have planetary gears, which complicates the drive system considerably. Swerve drive is a really cool technique. Each one of the wheels is independently steerable, so you can get it to do really strange motions because the wheels can all be turned in different directions. But one of the really cool ones is Mecanim. Mecanim was actually originally developed for forklifts by a Swedish company, and it literally, the wheels have rollers that are opposed at 45-degree angles to each other. So if you turn these two wheels, it slides sideways. So you can actually strafe along the wall with these things. So they're really great. The Navy uses them on ships because you can get into very tight places and then slide completely sideways with a forklift. So it's really kind of a cool thing. I do have a Mecanim bot. Unfortunately, my problem was I wanted to bring my big bots. But my big bots are literally like 120 pounds and 18-pound 12-volt sealed lead acid batteries. That TSA would not let me bring onto the plane. So it wouldn't fit in the overhead either, so it was a bit of a problem. All right, so which one do you pick? Well, it depends. The easiest, simplest one, skid steer. We have to think about wheels, and you think, well, how many options are there for wheels? Well, there's a lot of them. We have some simple plastic wheels. These are, of course, wheels like you would find on rollerblades. This is a holonomic wheel. So this one, it turns this direction, but you can push it sideways because these little rollers don't provide any resistance to sideways pushing. So for turning, it makes these holonomic wheels very easy to work with. You can turn four-wheel drive, turn with a holonomic wheel, easy. So you might find that you have a mixture. You might have some plastic wheels in the back, holonomic wheels in the front, and it's a very mobile robot. Doesn't have a lot of pushing power, so if you're going to get into a fight with somebody and you're going to try and push another robot around, holonomic wheels aren't going to get you much traction, but they're very maneuverable. This is that one I was talking about, Mecanim. So it's a really funky wheel. Each one of these rollers is at a 45-degree angle, and then they're matched on the corners. So the two corners will point the same direction. These two corners will point the opposite direction. So if they all turn forward, the bot moves forward. But as soon as one of them starts turning a different direction, the bot then starts swerving around all over the place. Really cool to watch it. I think I may have a video here. We can get to that if we have time. In most cases for this, in terms of a power plant, well, we could use a gasoline engine. Problem is gasoline, of course, is a nasty material to try and deal with, especially indoors. Your wife usually takes a very dim view of you starting up a gasoline engine in the house. So at least mine does, and therefore I typically tend to use DC motors. Of the DC motors, we have both brushed and brushless motors. Brushed motors are probably the easiest to get your hands on. They're also the easiest to work with. In the case of a brushless motor, we have to have a special device called an ESC, which is an electronic speed control, and each one of the brushless motors has to have its own ESC. And these ESCs start to become pretty expensive. So brushless motors, they're very cool, they're very quiet. This is what you would typically see for the quad rotor helicopters. They're all brushless motors. But in the bigger bots, they typically tend to be brushed motors because the brushless motors are very expensive as they start scaling up size. We can have motors with gearboxes attached. So that's a motor that has a gearbox directly attached to it. That's what these guys are. And then you also have, here's a motor. This is what's called a CIM, a CIM motor. It's about 1/4 horsepower. And you can get that motor, it's 12 volt battery, powers it, and you can get that motor for about, I think it's like 20 bucks for one of those motors for 1/4 horsepower. It will, however, when it's at full speed, pull upwards of 60 amps per motor. So you're talking some fairly substantial power draw. What you do is you take one of these motors and you tie it up with a gearbox. When you connect it to the gearbox, then you can gear it down through the gearbox. So you then make the decision as to whether you're going to go for speed or you're going to go for power. The higher gear ratios will give you more torque on the low end. They'll be very good on the low end, not so good in terms of speed. If you go the other direction, great for speed, not much in terms of power. So it depends on the kind of application you're trying to do, whether you need to push something around. For instance, if you wanted to make a motorized, certainly we in DC wanted this, a motorized snow plow. We had a lot of snow this year. Motorized snow plow, you would want low torque. You want very high torque on the low end. So you probably want to gear that gear the box accordingly. How do we deliver the power to the wheels? So the gearbox, there can be several different approaches. We can use a direct drive gearbox. This one has gears running throughout the gearbox. So it has connections for 2 of those sim motors. And then, so the 2 sim motors then drive, these 2 is driven by one motor, that one's driven by the second motor. So the 2 motors then drive all 6 wheels. But that's pretty heavy because even with the aluminum gears inside of it, that's a lot of gears. So the other option, of course, we can use belt drive or chain drive. Belt drive has the advantage that belts are light. These are usually timing belts that we're talking about, so they're very sturdy. You will get some stretching with the belt, but not a lot. It tends not to slide too much. The big weird thing is when you're chain driven, especially with a number 35 chain, you can actually, because the chain is steel, when you torque it back and forth, you start in reverse direction, the chain actually stretches. And it will stretch over time, so you have to actually put chain tensioners on it to make sure that the chain doesn't start jumping the sprocket. Of course, you remember on your bicycle, you have that weird thing, the derailleur in the back that keeps tension on the chains. Same sort of problem that we have with robots. So how do we control those motors? Well, most of the motors are going to be controlled through some sort of pulse width modulated signal. And the reason we use pulse width modulation is because what we would really like to be able to do is, say we've got a motor that runs from 0 to 12 volts. Well, we don't really want to try and figure out a variable resistor that could produce 6 volts or 7 volts. That's way too much trouble. And the resistor, of course, generates so much heat that it's really not practical. So what we do instead is we use this technique called pulse width modulation, in which case we have 0 and 12 volts. If we are off to on 50% of the time, it averages at 6 volts. So by using the difference in the pulse width, we can then determine any voltage from 0 all the way up to 12 by simply turning the voltages on and off really, really fast. And especially the motors themselves, they tend to be very tolerant of this to a certain extent. We do have to make sure that we have a high enough frequency going to the pulse width modulation that the motor doesn't actually detect that it's a separate pulse. Otherwise, the motor starts to chatter and it can get really nasty. It can tear a gearbox apart real fast. So these motor controllers, a lot of what we'll see are just basically running on RC servo motors. So the RC servo motors, as a matter of fact, this one is spinning. There we go, just started turning. The RC servo motors, it's a very, very specific sort of frequency. 1500 hertz is dead center. And it'll range from like 1200 to 2000, I think. And 1500 is off, effectively. So if you go below 1500 pulses per second, it goes backwards. Above 1500 pulses per second, it goes forward. This is a very standard sort of circuit. We see it used in a lot of hobby RC applications, aircraft, helicopters, that kind of stuff. And most of the servo motors all work the same way. They use the same RC signal. So a lot of the bigger motor controllers, that is, up to about 150, 160 amps, upwards of 200 amps in some cases, can in fact use standard RC servo hobby PWM signal inputs. And then what it does is we take the PWM here, we have a battery powering one side and the motor on the other side. Based on the PWM input, it will then take the 12 volts from the battery and then we'll output whatever variable voltage we want on the other side. Now these PWM controllers, these motor controllers, will typically be on the order, well, ones that'll handle up to about 80 amps will usually be in the order of about 50 to 60 bucks a piece. So again, this starts to add up. If you need 6-wheel drive, you need 6 motor controllers times 50 bucks a piece. That starts to get kind of expensive. Don't tell your wife how much you're spending on this stuff, or your significant other, as the case may be. Also, there's another one that's kind of coming into the forefront at this point. Of course, controller area network's been around for a long time, and we've been using it in automobiles for the past several decades. CAN bus is starting to become more and more prevalent on a lot of the SoCs. We're starting to see the IMX6, the Cortex M3, the Cetera parts, they all have CAN bus interfaces on them. So we can, in fact, output CAN bus, and a lot of these motor controllers have a CAN bus option available for them. So with CAN bus, it simplifies the wiring, because I can then have one wire that runs to each one of the controllers instead of a spoke of wires that comes from the central motor controller out to the individual motors themselves. So it can simplify the wiring considerably. But a lot of these other, like this one over here, this one happens to be called a Sabertooth. That one can be controlled with serial, I2C, SPI, USB, or hobby servo. And you just simply order it for the option that you want. On the sensor side, what kinds of things are we trying to sense? I mean, we're really trying to deal with alternative frequency domains. Either the acoustic domain, the light domain, maybe we're in the infrared or the ultraviolet domains. So we're usually dealing with how do we sense the world around us. We can, of course, use a camera, and I happen to have a camera on the front of this one. This one actually has Carl Zeiss lenses on it. It's actually a very nice camera. I have infrared. There's the infrared right there. These are sold as modules that you can basically say, I want a long-range infrared, I want a short-range infrared, and then you can attach them to little servos so they can swing back and forth and look for objects out in the field of view. Limit switches, they're basically nothing more than a switch that when an arm hits a particular position, the switch is engaged, you can tell that the switch is engaged, you know to stop. These are all techniques that we can use for closed-loop control. What we would ideally like to have is a situation where we're not simply, well, it should take 5 seconds to get to this point, and hope that the batteries are charged enough that it only takes 5 seconds. It might take longer, or it might take less, depending on the battery charge. So having things being timed, it works. That's open-loop control. It works, but it's not very efficient because we can't guarantee repeatability of the behavior. We have shaft encoders. Now, it's always fun to explain to my high school students what a shaft encoder is all about. It's a quadrature encoder. So basically, there is an optical mark on a wheel, and as the wheel goes around, you will have an A side and a B side. So we're getting nice square waves out of it, and if the A side leads the B side, I'm going forward. If the A side trails the B side, I'm going backwards. And they don't really understand exactly how this works until I hook an oscilloscope up to the robot and then start spinning the wheel. And then they go, oh, that looks cool. The first thing they said was, oh, you brought in a TV, cool. It's like, no, it's not a TV, it's an oscilloscope. But we also have acoustic. So this is an ultrasonic sensor. We have, this one happens to be a multiple degree of freedom sensor. It's got gyros, accelerometers, compass on it. Here's a shaft encoder over here. So you would literally put the wheel through that hole, and then this little wheel turns as the robot wheel turns, and then that will, you count pulses. So you'll have like 360 pulses per revolution. That says each pulse is 1 degree. And you know how big the wheel is, so you can calculate the distance that the wheel would go with 1 revolution Therefore, you can say, oh, if I go 5 revolutions, I've gone this much distance. That gives me repeatability that I wouldn't normally get if I just simply said, turn the motors on at 50% and let it go for 5 seconds. I don't know exactly where that would go in that case. Strain gauges, all kinds of cool stuff are available. And the neat thing is, from the Arduino community has really kind of jumped on the whole maker movement thing, and there are so many sensors available for Arduinos and Arduino compatibles, and there's source code available that tells you how to use them. I mean, it's really easy to work up a sensor package using a lot of these off-the-shelf sensors. And they're not that expensive. I mean, I have a 10 degree of freedom sensor on this one. It's got 3 DOF gyro, 3 DOF compass, 3 DOF accelerometer, and barometric pressure, and I think I paid $35 for it. It's I2C, which means I have to write an I2C driver for it, but you know, it's not rocket science. So our actuators and end effectors, what are we going to do with a robot? Are we going to have an arm that reaches out and unscrews the filler cap so we can fill up a satellite in orbit? Or what are we going to have? Is it going to be motor driven? If it's going to be motor driven, how do I get repeatability? Do I put limit switches on it? Do I put encoders on it? I could have pneumatic actuators. Pneumatics are great. They are very repeatable. They're very fast, but it means that I now have to have air storage and an air compressor on the robot. And then I got to plumb the robot, and I got solenoids and all kinds of other crazy stuff that goes on the robot. Pneumatics can be very cool, but the problem is they're either expanded or compressed. There's no in between. So there's only 2 positions for pneumatics, and that could be okay for some applications, limiting for others. We can, of course, put other energy into the system. We can have constant force springs. We can have surgical tubing. There's a lot of kinds of things that we can use to store energy inside of a robot. And then, you know, like a slingshot, we can just let the energy go and it throws whatever it's supposed to throw. Our control system, whether we're open or closed loop control, of course, is that thing I was just talking about. Do I have a way of being able to determine the absolute position in time and space of the robot at any one point in time? If I have that, I've got a closed loop control system of some sort in place. And that gives me that repeatability that I'm looking for if I want to be able to make this robot do something more than once. Yeah?
I should point out that one other way to get more or less repeatable is stepper motors.
Stepper motors, absolutely. Stepper motors have some distinct advantages. Stepper motors, the big problem with stepper motors is most of the commercially available affordable stepper motors are relatively small in terms of the amount of power that they will generate. So for some end effectors, stepper motors are very, very capable. For actually moving the robot, stepper motors, small robots, little bitty ones, yes. Big ones, no. All right, there's going to be some cases where I have some mixture. Maybe I have a limit switch, and maybe that's good enough. There will be other cases where I'm just going to run it by time because I don't have the time to sit down and actually put the sensors in place and wire them up. If I'm in the first robotics competition, I only have 6 weeks to build a robot completely from scratch. So oftentimes we have these wonderful designs for great sensor systems, and they go out the window because we get to the end of the build and we don't have any more time left, no way to run the wires, software has to be written and tested, there's just no time. So, you know, oftentimes we end up making compromises. Power is a big issue. So when we deal with power, we have usually batteries, and depending on the type of battery we're working with, we have, on my big bots, I use sealed lead acid. They're basically 12-volt motorcycle batteries, deep discharge marine type batteries that can, you know, do 80 amps at any one point in time. They've got great maximum current. Problem is they're lead and acid, of course. You definitely don't tell the TSA that you're, oh, this is sulfuric acid, don't worry about it. But the great maximum current. Nickel cadmium and nickel metal hydride, quick recharge. The problem with them is they tend to suffer from a memory issue. That is, they will look at how far you've discharged them, and then they'll start to remember that that's as far as they ever had to discharge. So they won't hold a charge forever. You know, usually for nickel metal hydride or nickel cadmium, you're going to have to throw it away about every year if you're going to play with it much. Throw the batteries away. Lithium ion and lithium polymer. LiPo batteries, they're kind of the darling right now in the quad rotor business, and of course with electric aircraft and things of that sort. Problem with LiPo batteries is if you discharge them really quickly, they have a tendency to catch fire, which definitely will ruin your day. They really have to be handled with care. Yeah?
You've got the explosion effect as well.
Oh yeah, yeah, no, it's, I did have one case where I had a LiPo battery that, you know, as it comes, red is always positive and black is always negative, except from this one factory in Shenzhen, where they shipped me a whole bunch of batteries that were backwards. Hooked up one of them, hey, okay, everything's working. Turn my back on it, boom, it exploded. Lithium everywhere. Everyone was very mellow, though. So, cool. Be very careful with, with LiPo batteries. That being said, I have an 8,000 milliamp LiPo battery in this robot. So it's definitely, you can get very big batteries, but you have to have special chargers too. That's the other issue. Nickel metal hydride, easy. You can go down to Radio Shack, pick up a charger. Any RC hobby charger will work with those. But with LiPo batteries, you have to have a special type of charger that does balancing across the cells inside of the battery. Otherwise, the battery catches fire. Don't want that. All right, power distribution. How am I going to wire this thing? How am I going to get power from the battery to all of the devices? Realizing that I'm going to have issues. Some of my equipment's going to be 3.3 volt. Some of it's going to be 5 volt. Some of it's going to be 12 volt. Some of it can handle up to 20 volts. So I'll typically pick a higher voltage battery, like a 3S or 4S battery, which is like 3S is 11.1 volts. And then I'll run it through transformers, buck transformers. And then that'll get me down to 5 volt, or I can get down to 3.3 volt. So you have the bigger batteries out there. They tend to be, of course, much larger. And usually when I'm running on my big robots, I have these guys. They're like 40 amp breakers, self-resetting breakers. Because if you get the motor into a stall condition where it's trying to turn and it can't, it'll draw so much current. I mean, the current draw goes exponential. And if you don't have a breaker in there, it'll catch fire. So that's bad. We need to make sure we use the right wire. And so these are the typical settings that we would have for different power draws. 20 gauge works fine for 5 amp. But when you're talking about powering motors, especially those quarter horsepower sim motors, you really think in terms of at least a 12 gauge or maybe as much as a 10 gauge in some cases. This happens to be a power connector called an Anderson power pole. I wish I got money from that. It's not me. It's not my Anderson, unfortunately. But these things are used quite a lot in the ham radio community. And they're very quick connect, disconnect, but you have to have the right crimp tool. So this is another one of those hidden costs in building robots. You have to have the wire, you have to have the connectors, you have to have the crimp tools. And if you don't have those things, yes, you can still build the robot, especially with the crimp tools. You can still build a robot, but it takes you 3 times as long. A good $100 crimp tool is worth its weight in gold. It'll save you so much time. So here's the general idea behind a block diagram of a robot. I've got my power source, whether that's a battery, what have you, going through some sort of circuit breaker. I have then power distribution, which then goes to the motors, the sensors, etc. Then I have a controller sitting out there with some sort of wireless bridge. I have my digital signals. I've got solenoids if I happen to be using pneumatics. I've got analog inputs. So I've got digital sensors, analog sensors. On the digital I/O, I've got my speed controllers. These are typically going to be PWM. I might have relays like the spike relays that we see in the first robotics competitions. These then go out to the motors and the lights. So that's the general idea. How you make that happen, there are a lot of options available to you. Because the computer hardware is cheap these days. That's one of the great things about what's happening with the introduction of all the SoCs. We can pick up a Beaglebone Black and it's really cheap, 45 bucks. You've got your Raspberry Pis at $35. You know, there are a lot of options that are available to you. And some of them are actually purpose-built. This one happens to be from a company called Fidgets up in Canada, and it has 8 USB interfaces on it because their sensors all tend to be USB-based. So it's real easy. Just plug in a USB cable, you're done. Makes it real easy to cable sensors in the robot. Of course, another company called Robotics, they also sell USB-based sensors. But the Minnow board, Beaglebone Black, Raspberry Pis, all of these, really easy to find. Whether you want to go ARM or you want to go x86 is entirely up to you. ARM will typically give you better battery life. Of course, I'm sure the Intel people in here are going, oh, that's not true. But I have seen people who have taken like laptops and repurposed the laptop to be a robot controller. It works, and it just depends on how much battery you've got with the device. So our software control, it turns out that Linux has a very rich set of potential software control systems. We have, of course, player and stage. There's the robot operating system, ROS, very popular. Oricos, which is what we use on this robot here. This is actually a robot that is on the Vomit Comet. So this is one of our robots that we built for testing in microgravity to see if we could refuel things in microgravity. So the plane goes up, it then drops at, for 30 seconds, and we're floating in space. And so is our robot. Definitely a very cool thing. Unfortunately, the people who were on the Vomit Comet, the reason it's called the Vomit Comet, you have to take scopolamine, is the drug that they hit you up with to keep you from getting violently ill. But then, of course, scopolamine is a truth serum, so don't talk to your wife while you're on that. You'll tell her everything. That's not good. No, not that I would recommend that you lied. We wouldn't do that. All right, so we have, so this one's based on Oricos. We have Robotics, which is a simplified Oricos. A lot of these robot control systems are very, very flexible. You can do anything with them. Unfortunately, they've become so unbelievably complex that it's difficult to get your arms around them. So some of the simpler ones like ROS and Rock Robotics, they try to make sure that they're achievable by normal humans. We have JAWS, Joint Architecture for Unmanned, actually it should be unmanned instead of unnamed. Of course, because it's mostly for the DoD, maybe they are unnamed systems. Maybe. So these are used for things like EDRIS, which is ordnance disposal robots, things of that sort. And then, of course, ad hoc, which is basically, hey, you make it up yourself. You can use Linux as a front end to front-end devices like Arduinos. We use the Arduinos to do what the Arduinos do well, which are turning motors and turning on sensors and things of that sort. And then we can use tools like Sear to Net to take the serial port output from an Arduino and wrap it around into a socket that can then be accessed via SSH or via Telnet. So it's a quick and dirty way of being able to get serial control remotely across a network. And, of course, leverage the Arduino ecosystem as much as possible. So to that in mind, I'll just go ahead and turn that on. We have a number of libraries that are available to us. I mean, the whole sensor system that I put together here, which has got an ultrasonic scanner that's swinging back and forth. It has 10 degree of freedom sensors. I wrote that at lunchtime. I mean, it's not hard to do this when you have the libraries and you know how the libraries work. We've got a lot of options available to us, either C, C++, C#, Java, what have you. And there are a lot of forums that are out there. If you go to places like robotshot.com, you can go to trossenrobotics.com. There are a lot of places. If you just do a little Googling, or if you're plugged into the maker community in your area, you will be able to find unbelievable sources of information and people that will help you actually build your robots, which is really very cool. Of course, you then can, when you're rolling your own, the one that I'll be showing this evening at the VOF is, it uses JS, it just uses the joystick software. I've got an Xbox controller, plug it into my, my laptop running Linux, and hook up the RF going across. In this particular case, I have this one running. Let's see if I can actually get it to associate correctly. Where is it? Beagle, where'd you go? I'm not seeing it coming up right offhand. Sometimes my laptop is a little recalcitrant at coming up with a Wi-Fi, but there should be a Wi-Fi running right now called Beagle, and I'm running host AP on this Beaglebone Black. So with that, you can actually come into the system and then get access to the camera that's running on the front there. Yeah, I've got lights on the camera. So I should be able to then get in and actually watch what the robot's watching. But just a quick check in a search engine will get you a lot of information about Linux robotics projects. Here's an example of all the controls that you would need to have. You've got your input device, your USB to the laptop, for instance. You've got a wireless router. I like to use the little TP-Link routers. They are very small. You can run OpenWRT on them. USB powered. You've got an access point and an Ethernet coming off of them. Great. They're like 25 bucks. Really cheap to get you Wi-Fi access. Yeah. Oh, I don't know. I don't think I should trust you with that because it's the robot is active, so you could drive it off, and that would be bad, I think. You can try and hack it, sure. So let's see here. 192.168.4.1:8080. Ah, there we go. And there's my stream. This is using MJPEG Streamer, by the way. So getting this to run on Angstrom was a bit of a nuisance. So I had to punt and switch to Debian. So this is running the latest Beaglebone Debian. And I'm running about 15 hertz on the refresh rate right now, which turns out to be a pretty good combination. You know, you want really high frame rates, but really high frame rates eat your bandwidth like crazy. So I'm running right now at 15 hertz, about 300 kilobits per second for that video. So I've got my speed controllers, my gateways, my webcam. This one happens to be a CAN interface. And then you've got a lot of these things that are available on the Android marketplace that are just ready-built robot controllers. A lot of them use Bluetooth rather than Wi-Fi, but it's not hard to then take the sources for one of the Bluetooth ones and convert it over to Wi-Fi. So is there a Linux robotics distribution? Yes, there are. There are certainly a lot of them. Ubuntu has a very big robotics community based on ROS. So does Fedora. So they are not specifically a Linux robot distribution. However, they have the packages. The repos are all set to be able to download and install things like ROS or Oricos or Rock Robots onto the platform without too much trouble. Of course, this one happens to be based on the Beaglebone, so I'm using the ARM distribution. You can, of course, get Ubuntu or Debian. And I had to switch over to Debian because the Wi-Fi access point is really goofy under Angstrom. So I couldn't get it to work reliably. It kept crashing the kernel. ROS, of course, probably the most popular one in the hobbyist robotics business. And it's really moving now into more professional robotics as well. So if you're going to pick one to look at the robot operating system. It's probably the easiest one, the most attainable, most understandable of the simple-to-use robot software out there, unless you're going to roll it yourself. And rolling it yourself, it's taken me about 3 days to roll a complete control system from scratch. So not terribly difficult, but you have to know sockets, you have to know I²C, you have to know a whole bunch of other things. So can Linux do real robotics? Absolutely, it can. These are a couple of our robots from our NASA work. This is a 7 degree of freedom robot arm. It stands about 6 foot tall, weighs in at about 1,000 pounds, and it's all being driven by Linux and the Oricos framework. And we're able to actually fly this and get very good repeatability out of it. We have taken a look. I mean, this is running preempt RT, obviously, so it's a real-time patch. But we've also looked at using Xenami underneath it. And Xenami really didn't get us that much extra. That was really something that we would go to the extra trouble of the complexity of Xenami. But certainly it's out there as a possibility. This one shows you the red here is the traditional Linux kernel as it ships. That's with the voluntary preemption. The green line down here, which has a little variability in it, that's the soft real-time low latency desktop option. And then the blue line down here is the preempt RT patch. Very deterministic, but not necessarily faster than the low latency desktop patch. So speed and determinism, not necessarily one and the same thing. Which language should you use? Well, of course, you should use C. But I know some of you are not going to do that. So, you know, Java, Python, a lot of people use Python. And it's, again, very attainable, very easy to work with. There are a lot of libraries available for Python, certainly Java as well. Some folks are actually using C# as well, although they tend to be Microsoft-centric, so I don't deal with them. So there are a lot of bindings that are available for these libraries. They all look like C bindings, so if you can do a C binding, you're good. So doing it under Android, also very possible using Jenny and reaching out to the native development kit if you're interested in doing it in Android. There are some good books that are pretty decent reference books. Robot Drivetrains is great if you're interested in how you trade power versus speed, torque versus speed. Building your own all-terrain robot, that one they actually show you using an old gasoline motor, you know, from an old lawnmower. I cringe at gasoline motors, because they're big, they're heavy, and they're explosive. Of course, so are LiPo batteries. And then Linux Robotics, also very good sources of information. So building a robot can be a lot of fun, be very rewarding, because it's great to be able to see something you built actually run across the floor or go across terrain. Make sure you use your web resources to keep track and keep from reinventing the wheel. I mean, there are a lot of people out there who've already blazed this trail. This robot, when I'm finished with it, I'm going to create an instructable that leads you through the whole process of how you set it up, how you load the distributions, what packages you have to load in the distribution to make it all work. So there'll be an instructable coming out that'll teach you all about how I built that one. And if you really like robots, I really would strongly suggest you think about becoming a mentor for our first robotics team. There are about 4,000 of them here in the United States, and an additional 2,000 or so internationally. So the UK, Netherlands has got a great team. We have Israel, several other places. And it's really kind of cool. Went to the regional in Israel, in Tel Aviv, and you had the Palestinian team were right next to the Israeli team. And they were helping each other with their robots. They weren't launching missiles at each other. That was very good. So very comforting. All right, so with any luck, I always try to get the freshest software possible, so I'm still working on the application for this evening. So hopefully it'll all be working by the time we get to the show tonight. But if you have any questions, I'll try and answer them. Yeah?
Would you mind if I put in the plug for the local robotics club?
Be my guest.
Okay. The local robotics club here in South Bay is called the Homebrew Robotics Club. It includes people ranging anywhere from 5-year-old kids working with Lego up to people who make commercial robots such as the Nido floor cleaning robots, competitors to the Roombas. He mentioned the ROS, the robot operating system, several times. Well, there are a few of the ROS developers who frequently attend the Homebrew Robotics Club meetings. And there will be a robotics club meeting tomorrow night, unfortunately at the same time as the Tech Museum thing. But let's see. Maybe if I tell you what it's about, you'll like it. Robbie Gagnon is going to discuss the Surface Telerobotics mission his team was involved in last summer, where astronauts from the International Space Station remotely operated a planetary rover, as well as the upcoming field test this October in the Mojave Desert of a newly acquired robot Trex 2 displayed at the Robot Block Party this year. That's all I got to say.
Last question. We're almost out of time here.
You mentioned going downstairs with the 6 wheels. How do you do that?
At an angle. Yeah, it's like doing moguls in skiing. You got to kind of take them at an angle. Otherwise, you'll flip over. Yeah.
US first a couple of times. As I understand it, the software development kit for that is a proprietary Wind River package.
Not anymore. This year, actually, for the 2015 season, it's dual-core ARM embedded Linux running Preempt RT. I was so happy. It took me a while to get that kind of pushed through. And there were a bunch of the mentors. We all kind of ganged up on US First and said, using VxWorks, hey, that's kind of cool, but that's also 1990s kind of technology. Let's kind of move it forward. Yeah?
Quick question about real-time requirements. When you have really fast real-time requirements for the closed control loops, I suppose that you go to microcontrollers. Linux can handle something that's a bit slower, but where do you draw the line from your experience?
The answer is, well, it depends. How fast is fast? If we're dealing in the millisecond range, Linux can handle that. Microseconds, yeah, you probably have to go to something else. But certainly you can always put more speed. That's the answer that the Intel guy had in the previous session. Just buy a faster processor. Okay, thanks.